In this lesson, we're going to discuss conditional statements and how they're used in geometry. So many of the theorems that we're going to look at are written in the form of a conditional statement, which is a statement that is written in if-then form. So we're going to take this statement here and we are going to put it into if-then form. So this is going to be kind of an unusual math lesson. It's all about sentences and how they're written. So this statement says all mammals breathe oxygen. So when you are writing a statement into if-then form, you need a hypothesis, which is the part that comes after the if, and a conclusion, which comes after the then. So in this, it says all mammals breathe oxygen. So I'm going to take the first part of that sentence, and I'm going to say if it is a mammal. So we can look at any animal and we can decide, or any species, and decide if it is a mammal, then it breathes oxygen. So we're kind of taking something and testing it to see if it will fit this conditional statement. So if it is a mammal, then it breathes oxygen. So the big part of conditional statements are that they are in this form, if then. So any conditional statement is kind of assumed to be true until you can find a counterexample. So a counterexample is one thing that matches our hypothesis but breaks our conclusion. So this says if a number is odd, then it is divisible by 3. So since the hypothesis of this was an odd number, what I need to do to break this conditional statement is to find an odd number that is not divisible by 3. And it only takes one counterexample to prove that a conditional statement is not true. So an example of a counterexample for this conditional statement, if a number is odd, then it is divisible by 3, is any odd number that doesn't fit the divisible by 3. So an odd number would be like 7, and 7 is odd, but 7 is not divisible by 3. So that works for any odd number that's not divisible by 3. It wouldn't have to be 7. So you could choose any odd number. You could choose 11. You could choose 5. Any odd number that's not divisible by 3 will be a counterexample to that conditional statement. So a lot of our postulates and theorems are written in if-then form. So we're going to start out with some of these postulates, our basic postulates. These are things that you probably would like to put on your reference sheet or in your mini notebook. So the first postulate here, it starts out with if there are two unique points. So unique meaning in different locations. So if there are two unique points, then there exists one line that contains them both. That contains them. So through any two unique points, there is only one line that can go through those two. So postulate 6 is going to go kind of the opposite way. So if there exists a line, then there are at least 2 points on that line. So a line is made up of an infinite number of points, but I know that there are at least 2 of those points to define that line. All right, postulate 7 is going to say if 2 lines intersect, then they intersect at a point. So if 2 lines intersect, and let's make this even a little bit better. Let's say 2 unique lines, because we're going to get rid of that by throwing in unique. We get rid of the infinitely many solutions when it's the same line. So if two unique lines exist or intersect, they intersect at a point. All right, postulate 8 is kind of similar to postulate 5, but with a different outcome. So if there are 3 unique points, then there exists one plane that contains them. All right, so if there are 3 unique points, then there exists one plane that contains those 3 points, and these 3 points are non-collinear. So postulate 9 is going to be the opposite of that. So if there exists a plane, then there are at least 3 points in that plane. So there are actually many, many more, but there are at least 3 points that are in that plane in order to define it. All right, another postulate says that if two if there are 2 unique points in a plane. So another way we could have said that is if there are 2 coplanar points, then the line that contains them is also in the plane. All right, so there's one more postulate on our next page, but notice that all of these have an if statement and a then statement. And the if came from this first image on the left. And then the arrow kind of shows like the change. It's kind of like the comma. And then the second part is the then. So a lot of things will be described in pictures, and then there's a conditional statement that goes with them. And the arrow only goes that one direction. So it always starts with the if, that's the hypothesis, and then it goes to the then, which is the conclusion. So we're going to look at one more postulate here on the back. So this one says, if 2 unique planes intersect, and that came from the first part of this image, and then wherever I see that arrow, that's like the comma. The next part is the then, it's the conclusion. So if 2 unique planes intersect, then their intersection is a line. All right, so that was postulate 11. So the next thing we're going to talk about are what you can do with conditional statements. And this has a lot to do with like logic and how it can be used. So what we're going to be doing is we are going to be negating some statements. So negation is the opposite of a statement. It is the not form. So another way, like if you are talking about like the statement, the hypothesis, which we're going to talk about these logic letters a little bit later, but if we use the logic letter P, which stands for the hypothesis, and then you put like a squiggle in front of it, that means to negate it. So that means to put the not form. So here are some different versions of that conditional statement that we can write. If we are writing the inverse of a conditional statement, that is a new if-then statement formed by negating the hypothesis and conclusion. So to look at this. I'm going to use an example and we'll look at what this means in terms of a conditional statement first. All right, the next one is the converse, and the converse is formed by switching the hypothesis and conclusion. So we're just going to flip the order. The then is going to become the if, and the if becomes the then. And for the contrapositive, that's going to be a conditional statement formed by negating and switching the hypothesis and conclusion. So for this, I'm going to first use an example from one of my favorite movies, and that is Mean Girls. So in Mean Girls, one of the main quotes that I love is, "On Wednesdays we wear pink." So they decide that on Wednesdays they're only wearing pink. So that is our original statement, and we're going to turn that into a conditional statement by doing if-then form. So we're going to have a hypothesis, so like if P, then Q. And so in logic statements, that's written as P arrow Q. So P is the hypothesis, Q is the conclusion. I'm not sure why they chose those letters. All right, so I need to take this statement and I need to turn it into an if-then statement. So it began with on Wednesdays. So my conditional statement is going to say if it is Wednesday. And then I always have to do a then. And so this is going to be my conclusion. So if it is Wednesday, then we wear pink. So that's our conditional statement. We have if, then. The inverse statement is formed by negating the hypothesis and the conclusion. So in logic notation, that would be not P, then not Q. So what this does is it takes the hypothesis of our original statement, if it is Wednesday, and we're going to do the opposite of that. So if it is not Wednesday, and then I'm also going to take my conclusion, which said we wear pink, and I'm going to do the not version of that. So then we don't wear pink. So I do the opposite of what it said. It said we wear pink. So the opposite of that is not to wear pink. All right, the converse statement was formed by switching our hypothesis and our conclusion. So we're going to switch it to where our conclusion comes first, and then we're going to go to our hypothesis. So it's still if-then form. It's just that where those statements go is going to be different. So I'm going to say if, and then I'm going to say my conclusion. So my conclusion here was we wear pink. So if we wear pink, and from there, I'm going to go to the original hypothesis, which was it's Wednesday. So then it is Wednesday. So those converse statements, you might notice that some of those postulates that we went through are, we have the first statement, and then the next one was just the reversed version. That's the converse. Now, the contrapositive is where you do both. You negate it like the inverse statement, and you flip it like the converse. So in logic notation, this would be not P, then not Q, then not P. So I'm really negating the converse statement, or I'm doing both. So I'm going to say not the end part. So if we don't wear pink, and then not P, then it is not Wednesday. And so in another lesson, we'll evaluate the validity of these statements and whether they're true or not. But for now, we're just focused on being able to write them. So the conditional statement is an if-then form. So if it is Wednesday, then we wear pink. The inverse statement is the opposite of what the original said. So if it is not Wednesday, then we don't wear pink. The converse just flips the order. So if we wear pink, then it is Wednesday. And the contrapositive does both. It flips the order and it switches the meaning. So if we don't wear pink, then it is not Wednesday. So that's kind of like a non-math version of the conditional statement and those other statements. All right, so here we have write the inverse, converse, and contrapositive of postulate 6. So on the previous postulates that we looked at, postulate 6 said if there is a line, then it contains at least 2 points. So here, if there is a line, that's going to be like our original hypothesis. It contains at least 2 points. That's going to be our original conclusion. So the inverse is where we negate both. So not P, then not Q. All right, so if I'm taking the opposite meaning, so if there is not a line, then it doesn't contain at least 2 points. All right, so next we're going to do the converse. So the converse was where we switched those two things. So instead of doing P to Q like the original did, I'm going to switch that around and I'm going to say the second part first and then the first part. So if there are 2 points and then I'm going to go to the original first part, then there is a line. And so that should seem familiar because that was postulate 5. The converse of 6 is 5. Oops. All right, so if there are 2 points, then there is a line. And then the last thing we have is the contrapositive, which did both. It switched the meaning and it flipped the order. So not Q, then not P. All right, so the contrapositive is going to change the meaning and flip them. So I'm going to start with the second part, which is it contains at least 2 points. So if there are not 2 points, then, and I'm going to switch the meaning of that first part, then there is not a line. All right, so those statements are not always necessarily true. We'll look at truth values later, but just as statements, that's how you write those. All right, the last thing here says true or false. If false, give a counterexample. So here it says 3 points are always contained in a line. So if we think through all of the possible configurations of 3 points and we determine that they will always be in a line, then this is true. So I want to start by looking at these 3 points. So if I draw them in a line, then they're definitely in a line. But it says 3 points are always contained in a line. So to make a counterexample, I just have to come up with one example where they're not. So if I just drag this one down a little bit into like a triangular formation, then since I have found a counterexample, this is false. And this drawing that I did is my counterexample. In that first thing we did, our counterexample was the number 7 because it broke the rule that it gave us. And here our counterexample is a drawing because we drew 3 points that can't be contained in a line because a line is in geometry it has to be a straight line, which means that it only goes in one dimension. This would have to go more than that.